Okay, so we're going to look at problem 9.44 here. It says to use source transformations to find the Norton equivalent or whatever. I'm just going to find a Thevenin equivalent, and I'm not going to use source transformations. So I hadn't finished writing this in yet, so let me finish writing some of these impedances in here. So we're going to find the Thevenin equivalent for this. Now, I'm doing this one on purpose here because this is very similar to how we'd find Thevenin equivalent of a circuit where we just have resistors, in the sense that, well, first you found the open circuit voltage, and then you found the Thevenin equivalent resistance. In this case, we'll do impedance. But when we just had resistors in the circuit and no dependent sources, we could just turn off the power supply and then find the equivalent resistance. It's going to be the same thing here. I'm going to just find my Thevenin voltage, but then I'll be able to turn off the power supply and just find the equivalent impedance, and that will be my Thevenin impedance. And so let's go ahead and get started here. So 100 at an angle of 90 degrees volts is what the voltage is here. So that would be J180 volts. Now again, if you can't remember how to do those here in your head, remember that 180 at an angle of 90 degrees is equal to 180 times the cosine of 90 degrees plus J times 180 sine of 90 degrees. And remember, that's my favorite equation, that Euler identity. That's where that's coming from. And of course, if you do that, you just wind up with J180. So, especially if you get an angle sometimes of like maybe 45 degrees or 60 degrees, I mean, you just do the same, you just do this formula, and you put whatever the angle is that you're given there. All right, so let's talk about the Thevenin voltage here. Well, the Thevenin voltage is plus minus the open circuit here, which is equal to my Thevenin voltage. Now, we should talk about the fact, though, that if I think about this capacitor here, in its current situation, what is, I'll call this I sub C. What is the current going through that capacitor? Well, because this is an open circuit, there is no current. I sub C is equal to 0. So if I label something here like plus minus voltage across the capacitor, voltage across the capacitor is going to be the impedance of the capacitor times 0. And so that's just equal to 0 volts. Which then means, since there's 0 volts across that capacitor, that means this resistor voltage here is equal to V Thevenin. Because this is important. The reason I'm going over this in detail is the next example we're going to look at. We're going to have something that we have to be a little bit more careful here. So the reality is, what we have here is that V Thevenin, which is equal to open circuit voltage, is equal to, well, let me draw the plus minus is a little bit different here. Let me draw the direction of this current. So do plus minus and the direction of the current going this way. V Thevenin would be equal to V open circuit, which would be the voltage across the capacitor plus the voltage across the resistor. But we just had this discussion that the current through the capacitor is 0, and over here, since the current through the capacitor is 0, that means the voltage across the capacitor is 0. So we end up with that this is equal to 0 plus the voltage across the resistor, which is just the voltage across the resistor. Alright, so we could go ahead and actually just do a voltage division here to get this, but I'll go ahead and write a node equation. It's not too difficult, and I think a lot of us tend to write node equations, so I'm going to put a node right here, and that's the voltage across the resistor is going to be at that node, because out down here, of course, we would think of this as ground. And so if we just write a node equation there, you would have the voltage across the resistor minus J180 divided by J30 plus VR over 15, and then that's equal to 0. And then we just have to solve that equation. So I'll work on doing it down below here. Now, just like we've done before, we would look at multiplying this by something. Now, in the previous example, I said, oh, I don't multiply by the j, and I'm not going to in this case. I'm just going to multiply through by 30, and then recognize I can just bring that j up into the numerator by doing a negative j. So what would we have here? Well, 30 times 30 is going to cancel out. So you'd wind up with negative j times the voltage across the resistor minus J180 plus 2 voltage across the resistor equals 0. And so what would we wind up here with? Well, we would wind up with negative j VR, and I sometimes skip this next step, but especially if you're wanting to be careful with your complex numbers, I'd have negative j times VR plus j squared 180, but j squared is negative 1, so you'd have negative j VR minus 180 plus 2 VR is equal to 0. So we'd wind up with 2 minus j times the voltage across the resistor is equal to 180. So then the voltage across the resistor is 180 over 2 minus j, which let me go ahead and do that computation real quickly here. So 180 divided by 2 minus j, and we get that this is 72 plus j 36 volts. Now, we often put this back into polar form. So if I go to polar form, and again just using my calculator to put it into polar form, this would be roughly 80, whoops, hello, my pen just got crazy there, 80.5 at an angle of 26.6 degrees. Now, as far as, and this is what Thevenin would be equal to. Now, as far as what would I want on an exam, unless the problem specifies how I want Thevenin written, I would accept either one of these as correct, as far as the way to write Thevenin. Alright, well then the remaining thing we need to do is find Thevenin, the equivalent impedance. Now remember, we turn off the voltage supply. So if we turn it off, it becomes a short. So I'm going to redraw the circuit as if I've turned off the voltage source. And so I'm going to have the inductor, which is now going to be in parallel with this resistor. And then I've got this capacitor. And then here are terminals A and B. And so we wind up with J30, and then 15, and minus J30. Now, of course, the J30 is in parallel with 15, so you can do 1 over J30 plus 1 over 15 inverse, and then let me do that computation real quickly. And if I do that computation, I get 12 plus J6. Now, what do we have here? Well, this is in series. That result would be in series with that capacitor, so my equivalent impedance would be 12 plus J6 minus J30, which would be 12 minus J24 ohms. Now, just like we did before, I always want us to draw the actual Thevenin equivalent. So the Thevenin equivalent here is going to be a voltage source. And of course, this voltage source that we had just computed is 80.5 at an angle of 26.6 degrees volts. And then we want to write down the components. Well, I'm going to have a resistor, and because I've got a negative imaginary part, that means I've got a capacitor. And so this would be 12 ohms, and this would be minus J24 ohms. And that would be my Thevenin equivalent circuit. And so when you're finding these Thevenin equivalents, it's the exact same process that we did previously for finding Thevenin equivalents.